All right, welcome back, everybody. So, in the previous video, we started talking about the Center Manifold Theorem and why we care about it. And we ended by talking about this reduction principle that's effectively, this is our Hartman-Grobman theorem for non-hyperbolic fixed points. So remember, Hartman-Grobman is saying that you can linearize around a hyperbolic fixed point and get the same dynamics as you would in the nonlinear system. And that completely describes what happens locally around a fixed point, a hyperbolic fixed point. But we didn't have anything to talk about non-hyperbolic fixed points, and this reduction principle effectively gives it to us. Right? This is our Hartman-Grobman theorem for non-hyperbolic fixed points. So we care about these center manifolds because they encode all relevant information, all long-term, I should say, all long-term information about the behavior of this nonlinear system, because all the nonlinear effects, all the stable and unstable pieces either contract toward or move away from the center manifold. So the center manifold does capture what we need or what sorts of long-term behavior we'd like to study. So, in theory, that's what this is supposed to do. But in this video, we're going to take a stab at some computational exposition and see what we can do with the reduction principle, how we can see it, how we can make computations in order to say what the dynamics of the system look like near a non-hyperbolic fixed point. So this is our computational foray. And first, we're going to go through a couple of things to be wary of, right? Books and references on center manifold theory are abundant, but they are often very, very dense and require a fair bit of differential topology just to get your foot in the door. So I'm going to see if we can't illuminate this without going into too much of that, too much of the graduate work that you would have to incur usually. So something that we see first, right, that is often discussed first, is that the local center manifolds, right, the WC loc, is not uniquely prescribed, right? There are actually a lot of different ways that we can describe a center manifold, right? So, for example, go ahead and consider this two-dimensional system. Uh-oh, did I run out of battery on my pencil? Nope, okay, we're good. Consider that two-dimensional system, and you can check. This is the bifurcating case, right? The non-hyperbolic system associated with a saddle node. Remember, I could do r plus x squared is equal to x dot, right? And if r is equal to 0, that's exactly the first equation in this system. So think of this as part of the saddle node bifurcation in 2 dimensions, or a saddle node bifurcation in 2 dimensions. Okay, so you can check the Jacobian at an arbitrary point in this system is this diagonal matrix, right? This is a totally decoupled system, and we're going to use that to our benefit here in a moment. But if we're plugging this in directly at the origin, which by the way is the only fixed point in the system, then the Jacobian actually is still diagonal, but it picks up a 0 along that diagonal, and that's what turns this into a non-hyperbolic fixed point. So specifically, the eigenvalues are 0 and -1, so there is a center piece corresponding to the 0, and there is a stable piece corresponding to the 1, but there are no unstable pieces in the Jacobian, right? So that would be how to identify these different n pieces. Since n0 is not 0, right, we do have a center manifold, right? So that means that this is a non-hyperbolic fixed point at the origin. So notice that we can go ahead and compute the usual eigenspaces. This is a diagonalizable system, so we don't have to worry about generalized eigenvectors. So diagonalize the system as you normally would, and you find that the stable eigenspace is spanned by 0, 1. The unstable eigenspace is trivial, and the center eigenspace is the span of 1, 0. So specifically, the center eigenspace is just the x-axis, and the stable eigenspace is the y-axis. All right. So if we continue, then you can actually check. In this case, it's a little tricky to check, but you can check that the stable manifold. So notice that I've dropped the loc here, and that's actually something that we do in text references all the time. That's something you see in text references all the time. It's very cumbersome to write loc every single time, so we usually just drop that notation. But the local stable manifold and the local center manifold, in fact, all of these manifolds for the nonlinear system are actually in line. They are the same as their linearized counterparts. So these are linear subspaces of R2. Now, to come back to the problem at hand, remember, we're trying to show that these guys are not unique. The center manifold is not locally. Locally, it is one thing analytically, but if you try to kind of expand out a little bit, there are many different ways to describe that center manifold with different approximations. So specifically, we're going to look at these guys, these phi alphas. And phi alpha of x is going to be defined to be effectively a solution to this system, right? If you think about dy dx as being y dot over x dot, then you'll wind up with the separable differential equation. X squared dx would be minus dy. And you can show that solutions to that equation are all of these. Like, this is a complete set of solutions to that system if we say that y of 0 should be 0. Right? We want to make sure this guy either limits on or has an initial condition that passes through the origin. Right? That'll match with the rest of the nonlinear system. But I digress. That's where this e to the 1 over x comes from, and we're going to make sure this happens for x less than 0. We're going to choose which side this solution exists on, and which side of 0 this solution exists on. And this non-trivial piece will be on the left side, and this is going to be a solution for any choice of alpha. And in fact, you can check the Taylor series on this guy, and the Taylor series is actually really boring for this. The Taylor series is actually the constant 0 function. Even worse, this guy doesn't have a non-zero radius of convergence. So this is about as bad as smooth functions can be, right? Where they are smooth, but they don't have a useful Taylor approximation. The only thing you know about it is what the function is at a specific point, but no other local information is known. So it's something that is not an analytic function. So it's smooth, but not analytic. But anyway, the local center manifold can then be approximated by any one of these phi sub alpha graphs. And I've just plotted down here one example in red, right? Any other choice would work as well. I could come at it from above here. I could come at it from below. I can come at it from way back here. All of these have the same approximation of the center manifold, or EC still approximates every one of these graphs. So, in other words, like, there is no one way to define WC loc. And a similar example can be shown, like, notice that this is occurring at a saddle node, right? That's exactly what we were saying up above, that this system is the critical system that separates the two sides, the two qualitative behaviors of a saddle node bifurcation. Okay? So, there is a similar example that we can do for Hopf bifurcations. Right, so this isn't like a dimensional phenomenon. This is just an inherent property of being structurally unstable. That these systems have a lot of flexibility to them, and that's something we have to work around. Second, in our list of idle curiosities here is that the tangent space approximation for the center manifold is not the center manifold approximation. And this statement stumped the living crap out of me when I was first learning this. I had no idea that there was a difference between these two things. I didn't even know that one thing even existed. I thought tangent space approximation is perfectly fine. We don't have to worry about a center manifold approximation because what the hell is that? No, in this case, I would like to make sure we distinguish between the two here. So the tangent space approximation is going to be our eigenspace approximation, right? So tangent space, remember, that's exactly what we're doing with the eigenspaces. This is a linearization of the local center manifold. So we are going to make sure that we make the distinction here. Based on the reduction principle, you might say that it's okay to just go ahead and use the center manifold vector and say that y has to be 0, and that the dynamics of the system are completely determined by what happens along the x-axis. And sad to say it, friends, that is just not the case. Right? You can show pretty dramatically that this is a bad idea. So if you were to go ahead and try to approximate the dynamics along this tangent space, you would come to the incorrect conclusion that this system, where I kill off the y equation down here because y is effectively constant, right? Y is constant along that system. But you come up with x dot is equal to minus x to the 5th. Okay, so specifically, this would mean that the origin is degenerate, but stable, right? You get a high order of contact, right? You get, what is it, 4th or 5th degree contact? What would it be? 5th degree contact. Or 5th order contact, because it's up to a 5th degree polynomial. But the point is that this guy, oh shoot, it's killing me. 4th degree. I can't remember if it's 4th degree because that's the last zero derivative, or 5th degree because it's the first non-zero derivative. Let me know in the comments if you know what that distinction is. I would have to go back and double check my notes on high order contact. But the idea is that if we were to make this approximation to say the dynamics of the original system are going to behave like a stable fixed point, no, it's not. You can actually plot out with a numerical approximation, right? This one is actually credit where credit is due. Perko, I'm using, I think it's the 2nd edition of that book. I pulled the picture out of that section, pulled a picture out of that book. Because honestly, the numerical approximation that I threw into my computer kind of seized up. It's hard to work with non-hyperbolic systems because they are inherently structurally unstable, right? You make a mistake, or you overshoot or undershoot a solution in a non-hyperbolic system or near a non-hyperbolic equilibrium, and you are going to pay for it dearly. Right? It's pretty nasty to have to work with these guys because they're not robust from a numerical standpoint. But I digress. This is the system that is the nonlinear system up top here. This original nonlinear system, and you can see we are coming in from the left, but going out from the right. So this actually behaves more like a saddle node than it does a stable node. So the approximation with the tangent space is a bad idea. Like, you don't want to use that because it's just flat out wrong in many cases. The vast majority of them, in fact. So the question now is, if we can't use the tangent approximation, we can't trust the reduction down to EC, then how do we compute WC to be more approximate or to be more accurate? Well, I'm glad you asked, hypothetical student. We're going to use the reduction principle to approximate the graph of the graph representation of this center manifold. So what do I mean by this? So again, remember, we can go ahead and reduce the problem down to the hyperbolic pieces of the fixed point and the non-hyperbolic pieces in the C matrix. So B is the hyperbolic pieces, and C will contain all the center pieces, or the non-hyperbolic pieces. But the idea is to use the reduction principle to show that the center manifold gets, through the implicit function theorem, a graph representation. So we're going to, oh geez, I did it again. We're going to use the fact that V is equal to the graph over U, right? There's over whatever U variables we want. We can represent this V variable, which in general is going to be a vector, not just a scalar function. So be careful. I'm not using the vector notation, but you should still be aware of it. The point is that I will get a graph that I can go ahead and either differentiate directly and come up with the left-hand side, or come up with the CV plus H portion of my equation, or of my system. Or I could back this up through the chain rule and say, okay, V dot can actually be expressed in terms of the Jacobian of capital V, and I have to multiply in U dot, and U dot comes from the top equation in this system. So I wind up with, if I use the graph piece, right, if I say V is equal to capital V of U, then let me see if I can draw your attention a little more directly, that if V is indeed equal to a function of U, then I can go ahead and say that these two red circled bits are actually going to have to be the same, right? So at least locally, I can go ahead and completely ignore these non-hyperbolic pieces and say that the center manifold is completely determined by them. And what we wind up with is something called the center manifold equation. This is a quasi-linear system of PDEs. And I'll be damned if that's not harder to solve than the original nonlinear system that we're dealing with. But the point is that we can use this guy to come up with a graph approximation of the center manifold, and this is going to be it's going to be exact. It's not going to be some tangent approximation that's going to fail us. No, this will tell us exactly the nonlinear dynamics that we need to know in order to classify the fixed point, or to figure out what the dynamics look like near that fixed point. So go back to this original system. Go back to x dot is x squared y minus x to the fifth, along with y dot is minus y plus x squared. And if I keep that equation on the screen, then we can go ahead and identify B has to be the center piece, right? Or sorry, not the center piece. It's got, yeah, the center piece. It's got to be this little bit of the of the center manifold equation, right? It has to correspond to the centerpiece of the fixed point. C is going to correspond way over here on the other side. Usually these are matrices. That's why I'm drawing, or why I'm putting them in little square brackets. Usually these are matrices, and again, we'll have we'll wind up with systems of equations rather than just a single equation. But the example we're doing here is supposedly simple enough where we don't have to worry about systems of equations, and we can actually make some progress. So with those linear pieces, G and H can be identified as these two pieces. They are the quadratic and higher order terms in homogeneous degree, or in total degree, I should say. Not homogeneous. Homogeneous means something else. But if we go ahead and plug those pieces into the center manifold equation, this is what we wind up with. And again, this is going to be an awful, awful equation to solve. This one is non-linear. Yes, it's quasi-linear, but that's still not much better. It is non-separable. Good luck. Try it. It's not going to be pretty. And this is just not pleasant in general to try to have to solve. So solving it exactly is out of the question. So what's the next thing that we do? Well, we recognize that this center manifold can actually be approximated with a Taylor series. Right? If it's smooth enough, if the dynamics are smooth enough, then I can go ahead and use a Taylor series starting at the quadratic terms, because we've already absorbed into EC the linear pieces. So y has to be quadratic to begin with. So if we want any degree of accuracy we'd like to compute, in theory, we can get to it. And in fact, this is a great opportunity for a computer to take over the computation, because what winds up happening here is you have to group by like powers in this case. So if I keep this equation on the screen, this red box, you can check, translates into the following equation. And the left-hand side, you can actually follow pretty quickly. The only thing that changes is that we add an x squared to the mix. So I get a 1 minus a times x squared minus a b x cubed minus a c x to the fourth, and so on. But on the right-hand side, this is where things get a little tricky. You're going to have to multiply. This is the FOIL problem from hell. Okay? So we really don't want to have to do too much work off of this, but we can get the low order terms. And low in this case means starting at 5th degree. If I look at multiplying these two terms together, they give me a fifth order polynomial. And everything else, every other term is going to have degree greater than that. Right? So this right-hand side starts at 5th order, which means, to me, that I can get away with murder on the left-hand side. And I do mean murder because I'm going to kill these two terms. I'm going to kill B and C. Right, go ahead, try to stop me. I dare you. Yeah, they're dead. Dead coefficients. Oh, we hardly knew ye. But the point is that 1 minus A here has to be 0, minus B has to be 0, minus C has to be 0, because I don't have those squared, cube, and quartic terms on the right-hand side over here. So, in particular, what I'm able to discern is that there is no cubic piece, there is no quartic piece, but there is a quadratic piece to the graph. And have a look again. Check this approximation. Remember, this is effectively y equals x squared, or y is approximately x squared. I'll be damned if that center manifold doesn't look like a parabola. Right? So this is exactly why we want to use the center manifold approximation, because it's going to give us a more accurate picture of the dynamics. In fact, it's going to give us a flat-out accurate picture of what the dynamics are doing near that fixed point. Right? And the trouble here, why we can't use that tangent space approximation, is because this is a non-hyperbolic fixed point, or it's a neighborhood of a non-hyperbolic fixed point. And we just cannot trust the dynamics of a linearization for a non-hyperbolic fixed point. And again, the credit here goes to Perko for the picture. Thank you, sir. And do beware of numerical sensitivities here. We are dealing with a non-hyperbolic fixed point, so this is something that is non-structurally stable, so the numerics are not robust. Do be very careful of missing or overshooting accuracy as your computer tries to plot trajectories. Usually Runge-Kutta methods are pretty robust in that sense, that if they do miss something, it's going to be minor and it should kind of recover. But man, it's a hard thing to do in a computer, hard thing to do accurately. So again, this is because we're dealing with something that is not structurally stable, right? So I digress. That's all that I want to talk about for the center manifold theory. There are projects that we can go over, or people can try for their class project, their final project at the end of the class, that relate to the center manifold theorem and how you might actually be able to use this to study bifurcations. right? The theory I don't think is too much more complicated than what's on this page of lecture notes. So if you feel like diving in a little bit further, be my guest. This is actually really interesting theory. It does get very computational though. So if anybody feels like maybe implementing a numerical scheme or some sort of program that will compute center manifold approximations, I think that would be another direction that you could take the project. And it would be totally worth it, totally worth your time, because that is a difficult thing to do by hand, and it's much easier to leave it to the computer to figure out. But I think we are now officially done with chapter 8. There might be one last thing that I want to say that does technically come from chapter 8, but really has more to do with chaos and what distinguishes this feature in chapter 8 from something that we'll see in chapter 9 when we start talking about the Lorentz system.